A model is a way of organizing our thoughts around a theory. Okay? It's a compact way of presenting a theory. So that's why mathematics is so useful. Okay, so welcome. Welcome to Introduction to Advanced Macroeconomic Analysis, better known as IAMA. My name is Michael Burda. I'll be teaching this course, and you'll get to know me over the next 16 sessions. I'm going to start right away with the material that is very fascinating to me, has been for most of my adult life, and it's about macroeconomics. So I'll end up having to define that at some point. But before I do that, I want to give you an outline of what I'm going to talk about today. So I'm going to talk about some administrative things because it's very important for us to be on the same wavelength in terms of what's expected of you. I'm going to talk about macroeconomics in the most general sense, what it is. I'm going to talk about theories and models because we do a lot of that in economics. It's abstract reasoning, and there's a reason for that. The reason is that we can't do experiments on human beings. It's not ethical. It's not considered to be ethical practice. Although some microeconomists do experiments, we can't do them with economies. We can do them with people who are actually willing to do it. And you can't just go and start a hyperinflation in Venezuela. Well, I guess you could actually. Some people have, but it's not something we want to do on purpose. Then I'm going to take you through the first model as a finger exercise. This is called the Solow-Swan or Solow growth model. Okay, this is a way of making concrete all the abstract stuff I talk about in the first few minutes of this lecture. And then I'm going to talk about economic growth, which, as Robert Lucas said, is one of the most fascinating phenomena of human existence. The fact that in the past 300 years, our material well-being has increased. This accretion to a material well-being has gone along with a lot of other things, including better health, better happiness, but also wars. So we have to be careful to just say this is great. Growth also causes pollution. And we know that Bill Nordhaus got a Nobel Prize for that just a few weeks ago. Very important issue that we'll talk about at the end of the course a little bit. The Solow model is a great way of introducing a lot of other things that are essential to macroeconomics. Concepts like the production function, the GDP accounts, what GDP means, what are the drivers of economic growth in the most basic sense? What is the Solow decomposition? How can we think about growth? And many of you are probably business interested. You want to go off and be a consultant. Some of these techniques you're going to learn are actually also interesting and useful in those applications as well. So I know some of my students have gone on to use the Solow decomposition to think about the way firms grow and why firms get bigger and why countries get bigger and why countries shrink, etc. So this is very, very important stuff, I think, for anyone who wants to call themselves an economist. Okay, so let's do those administrative details. There's a course description. There's some prerequisites. Obviously, you have to be a master's student. We do have people who are in other courses. That's fine. Other degree programs, it's all fine. You just have to get approval from someone, usually me, but also maybe your own Prüfungsamt or Prüfungsbüro, whatever it's called, in your school. And we also are on Moodle, so you can see there's a password. And if you want to get any of the information I'm talking about, you need to go to that Moodle page and log in and use this password. Okay? So that's to remind you who won the Nobel Prize in October. Early October this year. The most important part of this course is the final exam. In fact, it's the only part of this course. I mean, the way we are now constrained by our university, I may complain, if I may, about the way our university organizes the exam process. We're not allowed to test any other aspect of your ability. Okay, so this is basically your one and only chance to show how smart you are. A lot of universities in North America and England and UK and Spain, you'd be allowed to do problem sets and maybe show a little bit of what you could do and maybe sort of calibrate your own ability and then gauge on the basis of those intermediate measurements how well or how much you should study for the final. We can't do that. So we are going to have problem sets, but we're going to be giving to them in a completely optional way, but it will be only optional in the theoretical sense. I mean, you really have to work on these problem sets, and I'll tell you about that in a second. There's a final exam, and it's 100%. It's the usual 90-minute standard format. Now, Andreas hasn't shown up yet, so I'm going to introduce him in absentia, but it's okay. His absence will be documented on film for the rest of his life. It's really interesting. So, you know, what does Gorbachev say? What did Gorbachev say? Actually, Woody Allen said 90% of life is being there, right? So think about it. There are sections on Wednesday, and the Wednesday sections are organized around these problem sets. There will be 7 of them, and you'll work through the problems in the recitation or the section or Übung, whatever you want to call it. When I was in college, we called them sections, so I'll probably call it section or class. The formal lecture is kind of a broad brush description of what's going on, and then we'll get into detail in the section. And the problem sets are examples of using the theory, using the facts you've learned, the methods you've learned to solve real-life problems, okay? And I really urge you to do this in groups. Okay, so the idea of having groups to work on this will actually make a pre-assignment. If you sign up, we'll make a pre-assignment to a group, so you don't have to go around looking for people who like you or don't like you. You go into these groups, then you can sort of self-select into your own groups if you want. Okay, that's kind of the... I found this to be the most useful part about being a student, was talking to my peers who were equally interested in what we were doing, and then try to, you know, discover jointly what's happening. And this is part of the process. I mean, you can all be Eigenbrötler and do it all on your own if you want, but most people like the social aspects, you know, so this is really useful. So we have readings in this course. My slides are important. Most important are the articles on the internet and this book by Jean-Pascal Benassi. Part of the book's chapters will be put online, but we're not allowed to put everything online. That would be a massive copyright infringement, and Joan Pascal is a friend of mine. I wouldn't want to do that to him, okay? It's a great book, and I think it's, you know, you can actually buy it in PDF form. It's not that expensive. We'll try to make some of that available to you, okay? And of course, there's a course syllabus which has suggested additional readings so you can learn some of the stuff from the masters. So you can learn the Solow model by reading the Solow paper or the Phelps paper about optimal growth, the golden rule, etc. These are all things you'll learn about today. Or you can, you know, read some redigested version of that. Okay, but I would urge you, if you can, if you're interested in this stuff, by the end of 2-3 weeks, it might make sense to buy the book. You know, the great thing about the internet is it's created this huge market for used books. So you don't have to go through Amazon. You can go through all sorts of other sources. It's not a product placement. It's actually a negative product placement. Okay, so let's talk about the course in general. We're going to talk about growth, and we're going to talk about growth theory. This is about explaining long-run trends in economic development. One might say this is an attempt of economists to deal with the problem of economic development. We've seen a lot of interesting countries in the past 100 years. Some have gone down the drain, some have done very well, and some have been on top and have stayed on top. So understanding kind of the determinants of those facts and explaining the trends over time. When I talk about trend, I talk about a function of time and this evolution over time. Now that's one part of the course. The other part is about the day-to-day, quarter-to-quarter, year-to-year fluctuations around the trend. Okay, so we're going to talk about the business cycle. So the second half of the course is about understanding what's happening right now in the world, the United States, amazing run right now. Everybody thought the expansion was over in 2016, and now we've got a year and a half of more expansion. So how do we explain that? Is there any good explanation? What can economists add to our knowledge about that? And the fluctuation of other variables, not just GDP, but also things like unemployment, inflation, current account deficit or surplus, investment and consumption. We're going to learn a basic, very basic model as a background, but in fact this course is advanced. So my objective is to make you masters of this subject, because it's not accidentally called master's program. And that's important. So I'm going to teach you a lot of ways of understanding a basic picture. Okay, so by the end of this semester, you'll have many interpretations of what you learned as an undergraduate, the ASAD model. Again, models are ways of interpreting reality. They're not necessarily reality. In fact, they're usually not. And that's one of the reasons economists have a tough job. We really do. The microeconomists have an even tougher job. Okay, we're going to talk about things that matter no matter what kind of model you think about. Macroeconomics is about the future. It's about the future and taking decisions today. Okay, so everyone wants to know, what's wage growth going to be? Does it make sense for me to switch jobs? Am I going to get unemployed? Should I ask for a raise? Okay, or should I invest in this country? Everything is tanking right now. What should I do? So it's about looking to the future. And we're going to talk about different ways of interpreting the world. We're going to talk about two different growth models that have been made dynamic in the short run. One involves the role of technology, and the other involves the role of monetary policy and the banks. Okay, so it's a big chunk of stuff we're going to learn over the next 16 sessions. And I'd like to finish the course by introducing you to a concept which is a general equilibrium concept, thinking about many different equations describing different sectors and decisions in an economy and letting them work together in a general equilibrium, which is rather complicated. We won't necessarily be using the computer to do this, but we'll make it available to you if you want to choose to do that. This is a very important part for those people who want to go on to do more macroeconomics in their future. Okay? Any questions about that? This is all kind of general stuff. Yes? Can you speak a little bit louder?
Is there a date for the exam already?
Yeah, I think there is actually. He asked whether there was a date for the exam. Our Prüfungsbüro is incredibly efficient, as you probably learned already. These dates are usually established, so I would suggest you go and ask them. I don't know, but I will find out eventually. But I can tell you it's probably the first week of the post-semester period, which would be the third week of February. I can almost guarantee that, but I can't swear, okay? So let's talk about macro. So what are we interested in? We're interested in stuff that's like the bird's eye perspective. Okay, this is obvious. We're interested in aggregate activity. We're interested in something that's not just the sum of markets. It's actually more than that. And this is because markets interact with each other. So it's a descriptive, but it's also a predictive type of field. And part of what we'll do in this course is think about theory. If you took my course as an undergraduate, as a bachelor, you'll remember we did a lot of description and understanding how to measure things. Now we're going to invoke a fair amount of microeconomics to think about how these individual markets and decision makers interact with each other. So we have this super additivity or non-additivity of outcomes. And of course, we have to look at commonalities. What makes you do things? I mean, if you think the labor market in Berlin is going to get really good in the next couple of months, you might consider quitting your master's and getting a job. I know people are doing that. Okay, but it's based on an expectation. So where do you derive the information for an expectation? You talk to other people. You read the newspaper. What are interest rates doing? Is Trump going to put pressure on the Fed chairman not to raise interest rates? And what will that mean for Turkey? You know, these are really common experiences, common events that affect everyone's well-being. And that's kind of why we care about it. And that's why it's important to think about microeconomics, because each individual has a certain role to play in this additivity. Okay? So, in fact, we're interested in things that we can actually measure. So one of the things I like to stress is that this is about numbers. Okay, so in the rest of this lecture, I'm going to talk about GDP. I'm going to talk about what that means. Okay, there are three different ways to think about GDP, as you probably remember from your undergraduate course or courses. You can think about it as final expenditure, or you can think about it as the sum of all income earned in a geographic area, or you can think about it as the sum of all value added that an economy contributes as a flow in a certain period of time. So it's a flow. GDP is a flow. okay? Any master would understand that. It's not the same thing as a stock. Okay, it's like the bank balance, the balance of Dresdner Bank or something like that. But Dresdner Bank doesn't even exist anymore. Commerzbank, right? A snapshot. We're not talking about a snapshot, we're talking about a flow, like a river. Okay, so if you've forgotten about that, we'll think about it. We're going to be measuring this in some way to factor out the influence of prices, the influence of inflation, and that's where we speak of constant prices. And this is what national statisticians do all the time. They're basically valuing the value of goods and services in Germany. It's produced in a year, and they use a set of prices from the past to ask the question, how has the quantity changed? Because sometimes the goods change. It's very difficult to do this properly. And if you want, we can talk about it in detail. We're also interested in the rate at which the price of goods changes that doesn't reflect quality changes or the like. So at what rate is the money you're holding in your hands, in your pockets, in the bank, is it depreciating in value and purchasing power? This has kind of gone to sleep for a few decades. Probably in your entire childhood, you never used the word inflation. But if you were in my childhood, you would have used the word inflation. I remember a year in the United States when the inflation rate was 15% in 1 year. In Turkey right now, the inflation rate is pushing 70%. Okay, so there's a very interesting set of circumstances when we could actually experience this again. It might be interesting to find out why. What are the causal effects, the causal factors and the effects of inflation? And this feeds into finance. So a lot of you may want to go work for a bank. You maybe want to be involved in moving funds from one person to another, from one company to another. Then you want to consider this a very important aspect of macro, which is inflation, interest rates, nominal interest rates, stock market valuations, and then you're back in the financial market. Financial markets feed back on our behavior. So if you own stock and you're expecting to retire and the stock market crashes, then you've crashed as well. Your ability to move consumption into your retirement age has been attenuated, and therefore you're going to have to work some more, or you're going to have to go ask your friends for a handout. Okay, that's the way it is. That's why macro is kind of interesting to a lot of people who don't have a clue about macroeconomics. Okay, so this is a chance for you to make an impact. I already mentioned the unemployment rate. The unemployment rate in the United States has not been as low as it is right now since 1969. And for Hispanics and blacks, it's actually lower than it's ever been measured since the 1970s. These are remarkable facts. Do they mean anything? Just fake news? It's just some invented statistic? I'm sorry to say, but it's not. It's actually the truth. You know, the basis of the US unemployment rate is asking a person, what did they do in the past week? Were they looking for a job? Did they spend at least 1 hour looking for a job? They spend some time looking for a job? And are they working or are they not working? Okay, so that's kind of this is a basis for measurement that's also used in this country, although this country also prefers the measurement which appeals to whether or not you're getting unemployment benefits from the Arbeitslosenagentur, the Arbeitsagentur. These things are also important. They move around a lot. We'll see that later on in the course. People are also interested in the exchange rate. That's also a common variable that people face, right? So everyone wants to go to visit the UK has to change euros for pounds sterling. They're not going to accept euros except at the airport. So if you want to go buy a pint of beer, you're going to have to buy a pound sterling. What is the price of that pound sterling, and what determines that price? Okay, so to get a beat on this, we're going to start talking about economic growth. And I'm going to introduce a person whose name you will not forget. And then I'm going to motivate the Solow growth model. Okay? So this is the person, I'm one of my heroes of the recent 20 years, because I've gotten to know her a little bit better. This is Joan Robinson. So who was Joan Robinson? She didn't get the Nobel Prize. Okay, so in this male-dominated world, this was like a huge injustice. She was probably one of the greatest economists of the last century. Okay, she was a really difficult person, if you know what I mean. But she also had a lot of contributions to this course and contributions to the way we think about economics. Okay, so she was at Cambridge, a mother of the theory of monopolistic competition, which will figure in prominently at the end of this course when we talk about macro pricing models, price setting. I already mentioned this, but she was also a critic of what we do. So the interesting thing about her, and I think the reason she didn't get the prize is because she was very critical of what I'm about to talk about. Okay, so again, economics is this incredible mix. It's a melange of opinion and hard facts, and interpreting the facts in some way. So some people like Karl Marx said it was impossible to separate them. We're all basically apologists for the system. Other people, like myself, think you can actually use analytic tools to think hard about these things. And that's what I'm going to try to push today. Okay? But this is why you should remember her. Because if she's on the exam, she's probably going to be on in this form. She said the reason you want to study economics is to not get bamboozled by economists. Okay, think about what that means. You need to understand the way economists reason, even if you don't go on to be one yourself. Okay, because you will, I mean, you guys kind of belong to the masters of this university, and I hope, and I know many of you will go on to do great things, so I think it's important for you to get that one down. So, Joan Robinson, probably on the exam. There she goes. So, let me talk about theory and models. So this is one of my, a lot of people don't understand why I do this now. You'll see in a few minutes. But you need to ask questions. You know, why are we here? What are we doing this for? Why am I wasting your time? And the objective of looking at aggregates is twofold. One is to understand what are the facts? What are they? Do we have economic growth? And in what form does it take? What are the regularities across countries? Are there certain ratios of things that stay constant? What is the standard of living doing at the same time? Do we have a distribution problem? Do we have a lot of people getting very rich and a lot of people not moving at all? And once you've understood that and documented it and able to communicate that to somebody else, the next idea is to explain it. And that's the hard one. Okay, so the first one is like the doctor just writing down the symptoms. And the second part is actually using some body of knowledge to interpret the symptoms and conclude what's wrong, okay, and what's coming. Okay, so it's, again, a lot of what we do in economics is forecasting. We predict, conditional on stuff that we observe, that we can observe. So you can't predict everything. No one predicted that Trump would be president. Okay? But conditional on his being president, we have a whole bunch of stuff that we need to explain. Okay? So that's kind of the way economics works. We talk about conditional expectations, very important concept later on in the course. Okay, so let's look at what other economists have said about theory. Because model is an expression of a theory. And I'm going to define model in a fairly precise way. But we should probably start at the beginning. What is a theory? A theory is a way of trying to understand causal relationships. You know, if I stick my finger in the socket, I get an electric shock. Right? And to the extent that I decided to do that, I caused myself to get this electric shock. If I push this podium over, it will fall to the floor. Okay, that's a cause and effect statement. And economic theory is about trying to write down sensible statements about that. Okay, for example, what causes the hyperinflation in Venezuela? What causes long-term unemployment in Germany? What causes the Italian malaise right now? These are interesting economic questions that we'd like to interpret. And I think part of what we do is trying to write down the linkages. So this statement was made by a fairly prominent macroeconomist about 20 years ago who thought very hard about this. He's the editor of a very prominent journal. But this is not a new idea. This is a very old idea. Okay? So here's another one. See if anybody can guess who said this. The theory of economics does not furnish a body of settled conclusions immediately applicable to a policy. It is a method rather than a doctrine, an apparatus of the mind, a technique of thinking. It's a way of organizing your thoughts to help the possessor draw the correct conclusions. Okay? Anyone want to take a guess? Okay, yeah. Someone looks like he's going to raise his hand. Okay. Well, one of the most important contributors to this course, Keynes. And this is Keynes before he wrote the general theory. This is Keynes as a young man. Okay? So this is a very, very prominent idea. But it's really an idea that came about in the last, since Alfred Marshall, who wrote down mathematics, and maybe Cournot and maybe some other people, as a way of understanding the world. Okay? So you have to, why are we using all this mathematics? It's to help us interpret and make causal statements. Right? So a model is a way of organizing our thoughts around a theory. Okay? It's a compact way of presenting a theory. So that's why mathematics is so useful. It's an efficient way. So when I start talking about the Solow growth model, I'm going to talk about a production function. This is a way of abstractly representing how an economy is able, not necessarily will, but is able to transform capital and labor into output. Okay? That's kind of a statement of cause and effect. So it's an abstraction. And most important thing you can learn in this course is that models are not reality. It's not a way of displaying reality. It's a way of interpreting reality. So it's necessarily an abstraction. And you're smart people, otherwise you wouldn't be here. So being capable of abstraction is kind of what makes an intelligent person. To dissociate oneself from the unmittelbare Realität, the reality of a situation, and say, okay, I can think about this in more general terms. I don't have to look at Venezuela and Maduro and these things. I can think about a general country and a general set of circumstances. That's what abstraction is about. Okay? So there are lots of metaphors, and many of my colleagues use these metaphors, so don't think that I'm original in the sense that some of these are borrowed. Okay? But they're all interesting. Models are like a lens. If you want to look at something and you put on your glasses or you put on a rose-colored lens, you see basically the world through a filtration, and you're only seeing frequencies that are corresponding to the rose color or the purple color. Okay? You can put on glasses that completely filter out visible light but let in infrared light. Okay? So there are all sorts of interesting ways of filtering out confusing, confounding aspects of reality that just make us confused. We're not able to think about it clearly and think about the really important stuff. A lot of people say, one of my colleagues here in this faculty say that, and this is actually borrowed from a philosopher of the 1930s, the model is a map. Okay, no map is a depiction of reality, but it can help us navigate going from here to the Alexanderplatz or walking to Lüneburg. You know, a map can be useful. It can be a weather map. It can be a highway map. It can be a map of terrain elevation. They all have different purposes. So different maps have different uses. Today's model is a map for understanding economic growth. Okay? So a map. Model is also a window. Okay? It's a way of looking through something and looking into something. And it may be a black box. You know, if it's a black box, it's not a very useful model. You want to understand the causal elements and be able to apply this model to a new situation. So part of what you'll learn is whether it's a good idea, good judgment, to use a model in a different set of circumstances. Okay? And we will learn a lot of models today. In fact, Andrea still hasn't shown up yet, but part of what we'll do is give you a list of concepts that you want to learn by the end of the semester and the different techniques that go with those concepts. And this is a very useful map for you to get through this course. Okay, so what makes a good model? So we go into the philosophy of science, and we remember that there's a famous book by Popper and the philosopher of science, Kuhn, that basically say that it's all about falsifiability. If you cannot falsify a theory, it's not worth anything. So you, critical economists, should say, can I prove that this theory is wrong? Can I adduce evidence that would refute this theory? And if it doesn't, then maybe the theory is pretty good. But a theory that is vacuous and cannot be refuted is not worth much. We need to be confronting these theories constantly with new evidence and saying, okay, a great example is, how do you stop a hyperinflation? Do you turn off the printing press? Is that enough? Or is it enough to solve the deficit of the government that's behind this hyperinflation? Is it enough to fix the exchange rate? Is it enough to get an IMF program? What's the evidence? Predictions are validated, so we need to gather data. So we're a data-driven science. You can't do this in a vacuum. You need to get data. You need to understand what data are. Theories need to be logically consistent, and that's why mathematics is important. It guarantees that we have consistency because you know the assumptions, you know the operations that lead to the next step and the conclusions, and then you can basically decide whether the thing is logically consistent. One of the most important things about macro is that it's self-referential, okay? So we have a problem, we have several things going on at the same time, and the decisions made by some agents are conditioned by decisions of others. So by construction, we're solving a very large system of simultaneous equations, okay? Not necessarily linear ones either. So it's a complicated problem. Opens up all sorts of possibilities. We also want a theory to be simple so we can communicate it to other people. If you want to tell your friends, tell your grandmother about this, you better be able to explain it. And this sounds ridiculous, doesn't it? But it's not. Because we're so relevant to what the world does, we have to make ourselves understandable. Okay, so it's always useful to be able to explain to somebody in a bar, in a party, at a club, what am I doing? And why it's relevant for you. If you can do that, then you've made a big, important hurdle. Theories don't have to be realistic. So Milton Friedman, in his famous book on positive economics, makes this famous point that we see this guy who's an expert pool player, and actually, if you think about it, this guy must be an expert in classic mechanics. Every time he hits a cue ball, he must have solved all these incredible equations, including friction, etc. And because he's good, he always sinks the ball. How can he do this without recourse to really advanced, not just simple physics like we learned in high school, but like really complicated physics? Well, the answer is he doesn't. But might not be a good model to have to just assume that he does. If he's that good, and he's obviously figured out, he's internalized all the rules in his head, maybe that's a good theory. If it's just about predicting how he's going to behave, then maybe that's the right step. So this is a correspondence problem. We have a problem. There are many theories that can be equally valid in the sense of predictive ability, but some are just completely ludicrous. And then you have to decide, as a scientist, which one am I going to accept? And this may not mean to you much to you right now, but in a few weeks you'll know exactly what I'm talking about. Okay? So it's the usefulness, and again, it's a tension. The Germans have this wonderful word called Spannungsfeld. It's just, there is no obvious way to solve this problem. There are lots of different forces pulling one way or the other. And doing well in this course is going to be to understand what that all means. We can't use experiments. We can't experiment on people. Okay? So we have to use models. Models are like laboratories, and for the most part, models are deductive. So we make assumptions, we examine the logical consequences of those assumptions. Okay, so if I tell you that money is neutral, that means that if everyone understands that the money supply is doubled in all its manifestations, the price level must have doubled as well, otherwise people's behavior would change. Okay, that's kind of an assumption. And then we can derive certain implications of that neutrality proposition or assumption. But maybe people are actually blinded by the zeros. Maybe they don't get it. Okay? So something we need to test. You can also think of inductive models. So if you remember the famous astronomer Johannes Kepler, he spent 10 years of his life looking at the universe, studying the trajectory, his perceived trajectory of the planetary of movements and the stars through the sky, and deduced that the Earth's orbit can't be a circle. Okay, so it took a long time to write down the data and just basically use those observations to induce that the Earth's orbit can't be a circle, had to be an ellipse. An amazing thing. We do a lot of that in economics. Okay, so we don't really understand exactly the individual decisions of unemployed people to take a job or not, or to look for a job or not, but we can think about aggregate regularities. So the probability you get a job next year or the year after next will depend, in the abstract, on the ratio of open positions, vacancies, to unemployed people searching. That's an incredible regularity. It works for Germany, it works for the United States. Okay, so we can use that as a way of inferring some of the macroeconomic influences on your probability, unconditional, not knowing your personal attributes of getting a job. Okay, so you notice I use the word conditional, unconditional, really important. So here's some famous quotes, some famous people who thought about this. This is a Nobel Prize winner in the 1980s. So he thought the way we should do economics is just to write a computer program that maps one-to-one into decision rules that agents have taken or should be taking if they're trying to maximize utility or trying to maximize profits or if they're a company, and then letting those computer rules interact in some sensible way. This is exactly what we do. This is what we'll be doing at the end of this course. Okay? It's not exactly what you thought you were getting into. A lot of people like to use curves. Okay? So, you know, a method of reduction of reality involves using a two-dimensional representation of relationships. So like supply and demand. You've seen this before, right? Supply, demand. One of them. Okay? That's a representation of reality which works like crazy. It's great. 70% of the world can be understood with that diagram. Okay, you just need to know what's shifting the curves and what's causing the curves to be flat or steep. That's the hard part. Okay, so that's kind of what Robert Lucas doesn't necessarily talk about. So you need to think about reduction of reality. It's nice to have 15,000 equations in a computer model, but you need to also be able to communicate the essential aspects of what you're doing. And that's why maybe this view of the world is also true. Okay? So again, going back to Kepler, so this is not my original thing. Christopher Sims, a famous econometrician in the same decade, basically said that planetary orbits are not even ellipses. Okay? But again, ellipse is a better model than a circle. Okay? So it's a form of data compression. If you really put a microscope to it, you'll find that these ellipses are not perfect either. There's a lot of other stuff that we don't understand. There's probably some dark matter out there that's pulling stuff around. I have no idea. But the idea is how good we get to it means also how well we can convey it and convincingly represent these regularities. So theories can be so complex they do not allow this data compression. So we have this tension, right, between the inductive, this, and a deductive form, which would involve writing down a very thorough, exhaustive model of every person's decision in this room, which is completely ludicrous, right? So that's the tension that we have. So all that being said, let's talk about a model now. Okay, so I would really strongly urge you to take maybe a few notes. You'll get this immediately after the lecture, and you'll immediately be able to go and look this stuff up. And you are very lucky. Compared to my generation, I wrote everything down because there was no internet. I'm not going to post my lecture notes, but I'm going to post these slides. And if you find a mistake, that's great. You can tell me and then make me look stupid. But in the end, you've got to do some stuff on your own. And I think it's good to look at this stuff first. Okay, so we're going to talk about the Solow growth model as representative of model-based reasoning. Axiomatic, write down some stuff that we take as given, and then derive the logical conclusions, okay? And then test it with some data. And at the end of the day, today, I'm going to show you that this model, this Solow model, has a few holes, okay? Even though it's the leading long-run version of macroeconomics that we know. You go to any school in this country or in the United States or in Britain, Spain, you'll learn this model. Okay, call it the Solow-Swan model, with a hat tip to Trevor Swan from Australia, who actually discovered and published it the same year that Robert Solow did. Robert Solow is a really big name in economics. Nobel Prize in the 1980s, big guy, okay? But Trevor Swan actually wrote the paper in the same year, published the same year. It's a shame. Probably the penalty for being Australian, besides talking like this and ending every statement with a question mark. I can do this because I have many Australian friends. Okay, so this model can be found in my textbook. If you've never seen it before, you can look in Benesi for a very compact representation, and you can look at the slides, okay? This is a warm-up exercise, okay? This is a finger exercise for the next generation, overlapping generations models. So the research question of the Solow model is different from the research question posed by the OLG model, okay? But it's the same. Why do countries grow? What inhibits their growth? What accelerates their growth? And what does the dynamic to the steady state look like? The steady state would be some stationary situation where certain ratios are not changing, and I will define that in more detail in a second. So this is a great combination of two things, inductive and deductive. Okay, and I'll tell you why in a second, but you can already imagine. I'm going to assume some things, and then I'm going to look at the data, and I'm going to pin down some attributes that actually constrain my choice of models. Okay, so it's a great, finger exercise, so warm up for stuff we'll be doing later on. Let me motivate it first by talking about growth. So again, I don't want to bore you by putting some equations on the screen. First, let's talk about the growth phenomenon. This is like the most interesting thing you can think about. China. China has grown so fast in so little time. It will have a GDP per capita equal to Portugal's by 2030 if they continue to grow at the same rate that they're growing. There are parts of China that are richer than many parts of the United States now. And this has happened in your lifetime. When I first started teaching at INSEAD in 1987, I made the remark that if we could tap that market, this is how you get business schools students' attention. You say, if we could get all those people to use deodorant, what a market that would be. And I didn't realize how completely relevant that statement is. 1.3 billion people growing at between 6 and 10%. In the last couple of years, 6%. But since I've been teaching this course, actually more like 10% per year. If something is growing at 10% per year, how many years does it take for it to double?
7.
Good. That's a very important rule. It's the rule of 70. Exponential growth. It'll be on the exam. Seriously. Any master should know that. It's also true of half-life. So if something is shrinking at 10% per year, how long will it be half as big as when you started? Also, 7. Okay, in this section we'll go through the logic of the rule of 70. 70 divided by the growth rate. If it's a continuous growth rate, continuously compounded, that's a nice rule to know. It's very useful. So China, growing at 10% per year, has literally doubled in size in terms of GDP, okay? So Robert Lucas made this statement when China was just starting, okay? But you can see this everywhere, but not everywhere all the time. You see lots of exceptions. You see countries crashing and burning. And a lot of it has to do with politics. So we need to think about that too, right? The world isn't just economics. But if you look at like the 3 contenders of the European scene in the past 150 years, so we have this data from Angus Maddison, you can see this is his best estimate of total GDP for these countries, Germany, France, and UK, adjusting for borders, adjusting for the fact that Germany, back in the growth years of the 1950 to 1990, was actually just West Germany. So this is an adjusted value. But you can see that we've got something that looks like growth, and that's not enough because growth, because it's compounding, that picture suggests, actually, if you look carefully at it, that things have slowed down. Because if it's true exponential growth, it should be looking like an exponential curve. So how do I make sense of that? What's the first thing a good economist does with that picture? We're plotting GDP of a country or unit, some geographic unit, value added in a geographic region per unit of time. What would you do? Take logs. Take natural logarithms. It's a transform that everyone's Excel spreadsheet can do. The logarithmic transformation basically flattens out exponential growth. So if you're doing a consulting project for McKinsey, What is the first thing you have? You have to interpret 50 years of data for a country or for a company. The first thing you want to do is take natural logs and plot it on as a function of time. Or you use log paper, okay? When I was growing up, we used logarithmic paper, logarithmic scale. But now you just ask Excel to do it. You guys have it made. I mean, my dad had to use logarithmic slide rule. I had a calculator, right? You guys have a spreadsheet, so the world is moving fast. So learn how to do this. Take logarithms, okay? Because watch what happens. If you have something that's growing at a constant rate, it flattens it out as a function of time, right? The formula is easy. So if you just take log of this, you get log of x as a function of t is going to be a function of time. I'll show you the expression right now. So if you have a constant growth rate g and t is time, then the log of x of t is just gt. It's a linear function, and the linear parameter is the growth rate, okay? And it's the growth rate, technically speaking, divided by 100, okay? So logarithm looks like little tiny pieces, so you multiply it by 100, you get something that looks like a growth rate for small changes. That's called the logarithmic approximation, and you will learn that. It's really important. Okay, basic stuff. And it's the magic key to understanding a lot of stuff that's growing exponentially over time. If you want to understand China, you have to look at China right now, okay? Because China right now is huge compared to China in 1980. Okay, so, you know, how do I make sense of these changes? Well, if I take logarithms, then I'm looking at small changes, and logarithms are like percentage changes. And most of what we do in economics is scalable, and therefore susceptible to this type of analysis. Okay? Mathematically, if you take the log of something that's growing discretely, 1 plus g, next period's accretion being g, then that's approximately equal to g. So you can do this for price indexes, discrete measurements of the price level, and you can approximate and get the inflation rate. First differences in the logarithm of a price index is like an inflation rate. Change, the rate of change of that variable, okay? The same thing is true here. This is a manipulation that's used quite often. So I will use log instead of ln. Some people probably learned it ln or log base e. It's all the same for me, okay? So what happens if I take this picture and apply the logarithmic transformation to it? It's amazing. It flattens it out. And the remarkable thing is, you see that if you really, if you draw the line, it's a pretty flat line over the long haul. And we've got some pretty big disturbances here. We call them world wars. So war is not good for economics. Wars are not good, period. Okay, don't forget that. And you've got some financial crises here as well. But overall, the rate of growth of these three economies over the past 150 years is about 2%. And that would be the slope. That would be the slope of this line that I just drew. And I didn't use OLS to do that. You can do it. You'll probably get a number like 2.05 or 2.11 or something. Okay? And each country is a little bit different, but it's remarkable how similar France, Germany, and the UK are over the long haul. It's pretty remarkable. So that's something we're going to try to latch onto, this remarkable constancy of the past 150, 200, some would say 250 years of economic development. Some would even claim that growth rates have increased a little bit over the past 150 years. I wouldn't go that far, but let's take the United States now. Here's US data, fresh from Fred. So if you're interested, this is a private placement for Fred, F-R-E-D, Federal Reserve Economic Database of the Fed of St. Louis. So if you go to Fred, you can get it for free. Fred is free. You don't have to pay anything. You can get quarterly, annual, monthly data for anything you like, not just the US. So it's great stuff. Okay? So this is Fred telling me today what US GDP has done. So what do we see here? We see the trend. This is since 1947. So we see secular growth in the United States. We also see a couple of bumps in the road. Okay? A couple of them are associated with the oil price increases in the 1970s, so-called supply shocks. And we got a big one associated with the financial crisis, 2008. Big time. And what's interesting is that despite all the hype from not my president, but my current president, you don't see much recovery, okay? But again, if you take my word seriously, we need to take logs of this first, or use log paper, or ask Fred to do the log, or ask Excel to do the log, okay? And you get this, okay? So you see a constant trend up until the 70s, then you see a break in the trend, and you see another break in the trend. So this is something that really gets economists going. Is this for good? Are we in a new age of digital technical progress where things are growing more slowly? Certainly the oil prices had nothing to do with digital, but it had something to do with technical progress. So these changes, you couldn't see them if you looked at this picture, but you can certainly see them if you take logarithms, okay? So we do have something to explain, and I'm going to try to make the Solow point. So let me make another point. You can look at life in continuous time, point of time measurements. You can also use a discrete time measurement. So for this first part of the course, we'll be doing what's called continuous time. Today we'll do the Solow model in continuous time. So the notion is things are growing at some growth rate exogenously given to the model, and other things are going to be responding to that growth in different ways. Okay, so, but you can also think about a discrete time, indexing every observation with a discrete index, integer number, which would tell us in what period we're in. So in a quarterly world, like you'll be using in other courses, maybe other macro courses, you think of this as the quarter, 3 months time. You could also think of annual time, etc. And if you have that, everything goes through. You can take the log approximation just as before and get approximately a linear, or that's exactly a linear function of time because t is the exponent, but you get an approximation of gamma to the log of 1 plus gamma. For small gamma, that's a good approximation. Okay? That's why I said before, first differences of logarithms of some variable that's evolving continuously sampled or discrete time sampled with equal increments will have an approximation that changes of that logarithm are like a growth rate. Okay, so good students will learn and implement. If I want to measure the inflation rate of Germany real quick, I download the consumer price index, take logarithms of it, take first differences of logs. That'll give me a quarterly, if I have quarterly data, a quarterly rate. I have to annualize it, multiply by 4. Okay, again, this is basic stuff, but believe me, a lot of what you'll be doing in life, if you don't become a professor, is going to be doing basic stuff. So you need to be able to do this good, well, quickly. So you could do the same thing with these numbers, which is what I did. Okay, now I have lots of numbers. These are point samples, not equally spaced. Okay, and you can use the logarithmic transform these two endpoints and get an average growth rate, just like I said before. Okay, so we're talking about GDP, we're talking about value added at market prices, we're talking about, theoretically, the same thing, final sales within a geographic area, and it also means that all the production factors, all the labor and capital working in a geographic region have earned that. Now some of that capital might be owned by foreigners, and that's why it's GDP and not GNI. And I'm throwing this out because I know you're all masters. Okay? Otherwise in macro I would be spending half an hour explaining the difference between GDP and GNI. GDP is gross domestic product, geographically bounded, without regard to ownership of the factors. So think of Ireland, all those copyrights that belong to Apple and Starbucks, okay? That income is being earned by Americans that own those copyrights, but it goes into Irish GDP. Okay, so we're talking about GDP. It's easy to measure. It's a good measure of sustainable economic activity, but you could also think about it as income accruing to those factors that were working in that area, okay? We can measure it in current prices. That's the way our statistical agencies do it, but you also care about inflation, so you have to factor out the price. So we need to have a concept of price measurement. Okay, these are things that I teach you in Macro 1 in the bachelor program. This is stuff you should know. Okay, there's a Laspere concept, constant weights, moving through time, different prices. And then we have the Pasha concept, which says we use prices of a base year and price current GDP using those prices. That gives us the real GDP. Okay? So keep that in mind. We're going to use all the stuff I present you in the next hour or the next half an hour will be based on real concept. So we're factoring out inflation. We're talking about real GDP. German real GDP increases by about 1.5% to 2.5% per year in recent years. Some countries has done more, some less. We talked about China already. This is kind of a measure of production, economic activity. So you're asking me already, I see a lot of you kind of skeptical, you know, why is this important? Okay, well, GDP is correlated with happiness, strongly. Okay, and the best evidence of this is to look what happened to East Germany versus Poland, Ukraine, and Russia. Okay, who's had the big GDP development over the past 25 years? People complain about East Germany, but it's done very well. Believe me, I know about East Germany. And if you want to learn more, take my course, European Integration, and you can come with me to visit Poland and look at the factories. Okay? But the point is, GDP in East Germany is high. Material standards of living are high. People are happy. Now, it doesn't mean you can't be happier. Okay? And that's the next thing. Let's look at a happiness index across the world. This comes from my textbook. Okay? So you can see on the horizontal we've plotted GDP per capita. On the vertical we have the life satisfaction index, which is a very, very scientific survey controlling for language influences and the rest. You see that GDP is creates a lower bound. It doesn't make you happy. It means you have a potential for being happy, and you probably will be happy because you've got your basic wants satisfied, but you can be happier. So the real puzzle is, why are people so happy in Costa Rica, for example? Fascinating, right? That's something that a lot of economists are interested in trying to figure out. But you can see that we definitely have something like a lower bound here. So here we've got Norway, Qatar, Iceland, Switzerland, Denmark. The Danes are known for being very happy. GDP is also correlated with health. So countries that have lots of GDP can afford to take care of their people. Now, whether they do so or not is a political question. But if you look at East Germany, after the wall came down, they did much better. Women have the same life expectancy in both parts of Germany now. Not so for the men. Men in the East still trailing behind by a year. You can speculate why that might be the case. Okay, but it's an interesting fact. This is a fact. It's not a fake. It's not fake. Okay, so there's a reason to study GDP also in terms of trying to understand the human existence, the human question. So we're going to use the Solow model to think about this. I'm going to go fairly quickly. We'll spend some time in the section talking about it, and we'll also talk about it next week. Okay, so here's Bob Solow, Nobel Prize winner. His model shared with Swan, workhorse of macroeconomics. It's really the way we get our finger in the door, or get our foot in the door, to understand how the production potential, the potential output of countries grows. Okay, so we're not going to be talking about the cycle. This is not a model for the cycle. We want to block out the cycle. We want to look at the long-term, low-frequency development. Okay, why is China so much richer than it was in 1990? Okay, and I think the Solow model can give us a good handle on that. So I already told you that Trevor Swan got the raw end of the deal, but most people refuse to call it the Solow model without calling it the Solow-Swan, without mentioning Swan's name. Okay, so what are the building blocks of this model? The first thing we need is a relationship between inputs and outputs. And if you think about it, this is kind of close to a causal assertion. Okay, so the idea is, if you employ labor and capital, you're going to get some output. And the relationship can be summarized as a continuous function of those two factors of production. Okay, so we're going to start with this neoclassical production function. Okay, so we're talking about a capital stock. What is the capital stock? It's the stock of productive equipment, buildings, roads, infrastructure that are used to transform materials into output with the help of labor. Okay, so we think of this as called a value-added production function. We're not going to look at materials directly. It's not important in terms of economic growth. What's important is what economies have: capital and labor. L stands for labor. A stands for the effectiveness of labor. We call that technical progress, the state of technology, if you like, and A is growing at an exponential rate. Okay, this is called Harrod neutral technical progress. And it's one of three different ways of thinking about technical progress. I'll mention the others at some other point. Okay? So this is a way of understanding what goes in, what comes out. It's an efficiency statement. So in some sense, not every country has the same production function. And countries may lose effectiveness or they may gain effectiveness. If a country is corrupt, you can have the same amount of capital, the same amount of labor, and be very ineffective because people don't trust each other, they can't do transactions, the markets don't work, etc. So again, this is a reduction of reality into three factors: capital, labor, and the effectiveness of the way economies put those two factors together to create welfare, well-being, economic prosperity. Okay? So I need to make some assumptions about that function. These are really basic, what we call neoclassical assumptions. First off, the function is a positive function of both inputs. Okay, so that means that if I increase K, I'm going to increase output. If I increase the labor input, AL, the product of this technical effectiveness or efficiency times the labor input, number of hours, I get more output. I'm going to assume constant returns to scale, which means if I double everything, I'm going to get double the output. It's a scalability assumption. Okay? And evidence seems to show that within the range of what we observe in Germany, for example, that's a pretty good assumption. If you need evidence of that, think about Luxembourg. Luxembourg's a really small country, but it's really rich, really productive. Ireland, very productive. Germany, very productive. Okay? So scalability is not a first order importance to us in this Solow model. We're going to focus on two factors, this abstract AL, which is effective labor. Think of it as a technical progress form that makes you just more effective over time. So as if you're working in a factory, and as you accumulate knowledge, etc., in an exogenous way, you're becoming more effective. So it's like multiplying your body or your number of hours that you're working by factor A. Okay, so we'll see that's a very important assumption. It's actually one of the most interesting regularities in economies today, is the fact that most of what we observe in terms of productivity augmentation is coming from Harrod neutral technical progress. Not necessarily all, because the digital revolution is causing issues about that. So if we have time, I'll talk about it, maybe tomorrow, next week. Okay, but it's important to think about, over the past 100 years, most of technical progress has the form of being Harrod neutral technical progress. Okay, and there are lots of fancy things I can tell you right now, but I'm not going to tell you now. I'm just going to, that's kind of the basis of the Solow model. So we're hardwiring it into the production function. The production function becomes more effective because A is growing exponentially over time. Okay, that's what Solow's most robust contribution, if you read his 56 paper, was exactly that. Yes?
Just a short question about how technological progresses in general. So it's very intuitive if we think about it during a lifetime, someone gets knowledge and age improves, but what's about think of 200 years?
Yeah, okay. Well, again, this is a great question. This is a great question, and the beauty of the Solow model is trying to cook it into something that we can get our hands on first. But his question was, how do we think about A? What is it? Okay, well, it's the body of knowledge that can be transferred, that has no cost of transfer, or if it does, it's something that people are doing in a regular way. So human capital, passing on your knowledge to your children or to your colleagues at the workplace. You're training somebody, I'm training you. That's the way we like to think about this. It turns out this is one of the most important sources of long-term economic progress. We'll see that in a second. Okay? Now, I'm going to restrict this even further. I'm going to say, if I divide this function by AL, I get what's called the intensive form. Okay, it's like capital per unit of effective labor. So if A were equal to 1, it would be just capital per unit of labor. This turns out to be a sufficient statistic for the source of economic activity. So countries that have lots of capital per capita tend to be more productive, richer, more prosperous than those that don't. So that's an initial observation that just comes from the production function. Okay? So if you want to make Albania look like Germany, you're going to have to install a lot of physical capital in that country, because the data right now show that Albania doesn't have much physical capital. Okay? That's a fact, but it could also be because Albania and Germany have different production functions. Okay? But again, for a given production function, little k, which is equal to k divided by A over L, is a concave function. We'll draw that in a second. Now, if you like math, these are the mathematical correspondences to all the stuff I just said. Okay, so it's a continuous function. Has a 0 at 0, 0. So if you don't have anything in, nothing in, nothing comes out. It's kind of logical. The partial derivatives summarize the marginal effects of changing the inputs. And the second derivatives capture what we call decreasing marginal product. Okay? So if you put in more capital, you get more output, but you get less and less at the margin. That's a neoclassical production function assumption. It's a neoclassical assumption. It's what kind of Adam Smith kind of danced around, but later Marshall made it concrete. Okay? Constant returns to scale can be summarized in a very simple proposition. For positive t, if I scale up stuff by t, I get ty. Okay? Again, it's an assumption. If you buy that, then it turns out that this holds. If I multiply the first derivative of f with respect to k times k and add it to the first derivative of f with respect to L times L, I get y. I exhaust output. Okay, so this is called Euler's theorem for homogeneous functions of degree 1. Fascinating. Well, if you remember your economics, the marginal product of labor in many of our models is equal to the wage, and the marginal product of capital is roughly equal to what? The rental rate on capital. So this means that if you multiply the respective factor prices in a competitive economy times the factor inputs, you exhaust output. It all gets paid out. There are no excess profits. Okay, so this is a fairly interesting, controversial, if you like, also aspect. The last statement I made about concavity means that if I plot the intensive form of the production function, it's going to look like this. It's going to have the bow shape. Okay, and there it is. That's what it's going to look like. Little k defined as big K divided by A times L. So it's capital per effective unit of labor. If you set A equals 1, it's capital per unit of labor. Okay? So note carefully, this is an interesting, compact statement of everything we've talked about until now. Okay? We've basically said an economy that has endowment of K, little k, and uses it, it can reach this output per capita. So you see, one obvious conclusion is that rich countries have more capital per capita. They might, for a given production function. And again, it's hard to imagine what that means, but look at Poland and Germany. Poland and Germany have pretty much the same human capital. Education is pretty comparable. Okay? You might make the argument that the Poles can do everything the Germans can, okay, but they don't have the capital. And to get the capital, they need to save, they need to accumulate over time, or they need to get FDI from Germany. Okay? So it's a nice way of understanding why the slope of the ray that goes from the origin to the point of interest is equal to the capital efficiency of an economy. Okay, so if you think about it, y over little k is the same thing as big Y over big K. Okay, and you can see that as you get more and more capital, you become less efficient. So in Germany, we have lots of capital. We have lots of highways, lots of this and that. We have lots of machines. Okay, so the productivity of a machine on average is lower than it is in a country that has less capital. Super interesting insight. But of course, you know, neoclassical economics is more about the margin, so we care about this one. We care about the slope of the curve. Right? That's the marginal effect of an additional unit of capital. And you can see that that thing is decreasing as I push my little k out. The more capital I use in production, the less productive it is at the margin. So let's use this together to do the Solow model. So I'm going to move a little bit faster now. Okay? Growth comes from three things: growth of labor, growth of capital, and growth of technology. The Solow model is very simple. Three sources of economic growth. Growth in inputs. I'm going to make life easy for you. I'm just going to assume that the economy's growth of population is exogenous. Okay? It's given basically by some base number of population times a factor, Euler's constant raised to the nt. Okay? So the longer you've been there, the bigger your population is going to be. This can change, of course. So better models, more interested in population, could focus on those aspects. So we're going to think about labor growth, growth in labor input, whether you measure it in terms of hours or people, is going to be growing at rate n. We're going to have exogenous technical change. I already told you, that's the last line. So AT, the state of technical progress at point t, at time t, is equal to some base period times Euler's constant raised to AT. Okay, so A is an important number. Little a is the rate of growth of technical progress in this model. The most interesting thing about Solow is he's telling us about how you get the K. Right? So how do countries accumulate capital? So Marx, you know, no slouch, observed correctly that capital is the whole story. It's about who owns it, who accumulates it, who uses it. But you can be a neoclassical economics guy and still get that one. Okay, so the Solow model is about accumulation of capital. And where does it come from? Where does capital come from? What is capital? Okay, this is where this is where Solow really broke through and taught us something very important. So capital accumulation is basically a race between gross investment and depreciation. Okay, so this building, when I first came into it, to the Humboldt-University in 1993, was a disaster. Okay, it had been depreciated over the past 80 years by various regimes. Okay, it needed a paint job, it needed to be renovated, and you can see it looks pretty good now, doesn't it? If you want to see how it looked, just go out there and look at those pictures on the walls. Okay, so investment was necessary to spruce up this building, make it look presentable and usable as productive capacity for the economy. Where did that stuff come from? In the Solow model, it comes from non-consumption. An economy that's ready to give up some consumption can accumulate capital. That's the bottom line. Okay? So capital accumulation is endogenous. It comes from the fact that people have deferred at some point income that they could have spent on consumption. And in a closed economy, there's no other place they can spend it. So it's a nice way of thinking about the wealth of nations, if you like. But we need to think about the savings decision to understand why the Solow model is so important. Capital accumulation occurs through deferred consumption. And that's a lesson we'll learn for the next hour as well. Okay? More capital per capita can only be accumulated if people are willing to save more out of current income. So we need to understand where the capital comes from. So Solow's contribution was to assume that savings is endogenous. So that's Andreas. Why don't you stand up and... Yeah. So Andreas will be doing the section tomorrow. So please be there. So Solow's contribution was rather mechanical, but it's actually empirically pretty accurate. He basically postulated that savings was a constant fraction of income. And in this model, this closed economy, income is equal to output. Okay, so little s is the savings rate, an important parameter in the Solow model. So we've already got technical progress, we've got savings behavior, capital accumulation. We'll see that depreciation is important. In this diagram, I'm going to be looking at points in which little k and y stop moving. So the next couple of pictures I'm going to show you are to asking the question, at what point does the capital stock per capita or per effective unit of labor, because I'm using AL as the denominator, stay constant. Okay? So think about it. What is savings? Savings is S times Y. What is capital doing? Capital is accumulating all the time, but it's also per capita, per effective unit of labor, it's also going down because the more people we have, the less capital per capita we have. The more technically advanced we are, the less capital per effective unit of labor we have. So it's a race. And then you'll have depreciation as well. Think about this building. 80 years of depreciation meant this building looked terrible. So to get it back to the state that it had in 1905, you had to do a fair amount of investment. So the equilibrium condition we're going to be looking at basically asserts an equality between the savings that households are willing to bring to the table and the amount of capital that needs to be replaced for the capital stock per capita to stay still, just to stand still. And I'm going to show the diagram in a second. This is just a way of getting you tuned up for this. Remember, in this model, we've got output growing at a rate, and that's going to be related to the rate of technical progress. It's going to be related to the growth of capital accumulation, the rate of growth of labor accumulation. But we care about output per unit of labor, and we care about output per effective unit of labor. Those things are going to have different properties. And that's why we need this picture to show them. Okay, so I'll show you that picture now. And the driving, remember I told you at the beginning of the lecture that we combine deductive and inductive methods. So, you know, this model is very, very expansive. It can do lots of stuff. But you need to discipline it. And one of the things we're going to use is that a famous economist by the name of Kaldor said that we noticed that these countries that we're looking at, that I showed you before, they all have the property that K over Y, or Y over K, is constant. Okay? Even though we have growth, you saw the growth pictures, output per person is rising almost without bound, we still have the fact that in these models, in these data we're looking at, measurements of capital and output, the ratio is very stable. Okay? So that's called the Kaldor fact, one of many facts. And we can identify that in our diagram, because the ratio of little k to little y is equal to the ratio of big K to big Y. Okay, so I'm going to be looking for stationary states disciplined by fact, because Kaldor showed us with 100 years of data that these things do look steady. When a country has reached its sort of steady state path, you have this constancy of K over Y. It's very interesting. I looked at Germany, for example. East Germany has a very similar K over Y than West Germany does, even though 40 years ago that was certainly not the case. So because of extreme development, East Germany has moved very close. In fact, in some industries, it's actually more capital intensive than West Germany. Interesting, right? So again, we need to think about technical change, and that's going to also contribute, and that's why we do this this division by AL. It reduces the basis of the model to a per capita or per effective capita basis. Okay? So we're going to focus on those steady states in which K and Y are growing at the same rate. Kaldor fact, Kaldor steady state. So here's the model. I've now interacted this production function with two other curves. The first one is the savings function. This is just S times little f. Okay, so it also inherits the same properties of the production function. It's just the production function multiplied by S. Okay, it's basically the amount of savings that households are willing, and firms, because firms are also owned by the households, are willing to generate in a given period of time. Now, there's not enough information in those two curves to determine where the economy is. We need to know how much capital does an economy need to stand still to fulfill the Kaldor fact. We call this the capital deepening line. That's the ray that's emanating from the origin with slope depreciation rate of capital plus the growth rate of the population plus the growth of technology, technological change. Those three determine the slope of the capital deepening line. Okay, so basically the model Again, model generates a clear, crisp prediction that economies that have a slope of their capital deepening line of this extent will basically stop accumulating capital when K star and Y star have taken these values. That's why we use the star, the steady state. And you can read off the production function, capital, given capital per capita, or capital per effective unit of labor, Y star, which is output per effective unit of labor. Now note at this point, there is no growth in capital per unit of effective labor, but the economy itself is growing. In fact, it's growing at the rate of the population growth rate plus the growth of technological progress. And per capita income is growing at the rate of A. Okay, so in the section we'll go through this in detail. Again, I'm not going to, this is a finger exercise getting us into the habit of using models. But one of the reasons we use models is to make predictions. So the obvious thing you want to ask this model is, can I predict the outcome of an economy that's changing something that we thought we considered to be parametric before? So this is something you learned today, comparative statics analysis. What happens if I change one of the little parameters of the model? What happens to the outcome? Okay, this is called comparative statics because we're comparing two static equilibria across different parameter values. So what are the parameter values in my model? I have lots of them. The savings rate is the most obvious one, but also the rate of population growth, the rate of growth of technical progress, the depreciation rate of capital, which can change over many, many decades. If you just build buildings, the depreciation rate is low, but if you're using software is a form of capital, it has a very high depreciation rate. Okay, so this is obviously a very interesting parameter to change. Okay, you can also move outside the Solow model. The more advanced version of the Solow model, you could put government in there, you could have government infrastructure, you can have labor force participation. Don't do that. Just stick with what I'm doing right now. I'll give you an example. Okay, so the best example is what happens in this economy, starting from this resting point, K star, Y star, if the savings rate increases. Everything else is the same. Comparative statics. The Solow model is exquisitely equipped to answer that question. Okay? Again, you can use a graphic analysis or you can also use math. Okay, in the section we'll take you through the math, but it's very easy to do it graphically as well. Okay, so starting from this point, the question is what happens if the savings rate moves from S1 to a higher level S2. Let me just tell you an example. Germany's S is about 25%. China's S right now is about 40%. The United States is more like 20%. I'm not just talking about the households, I'm talking about households and the firms that they own. Okay? And in fact, if you consider government, you also have to add in the government deficit or surplus. Okay, but just in the Solow model, we don't have any government. In fact, this is all a very sort of a highly aggregate analysis, but we can already start making statements. So what would happen if the savings rate increased from S1 to S2? The production function doesn't change by construction. Everything else is held constant. Okay? Savings function shifts upward, and you can see immediately that the economy is now accumulating more capital than it needs to stay at the Caldor steady state. So we have a growth process that sets in. Okay, so delta K is positive, okay, by that amount. And when delta K is positive, little k, that means that the K will move from K star to the right. So we release the force of capital accumulation, which moves us to a new position in this diagram. Okay, in fact, it will move us to if you like, Y star prime. Okay, so the process of moving from this point to this point is a short to medium run adjustment of the economy to its new equilibrium. The new equilibrium says they're still growing at the same rate as before, but GDP per capita is permanently higher. So the Solow model is an excellent way of making prediction, you know, why is Germany just richer than a comparable country in Southern Europe. Because there's no one's going to tell me that Spain has an inferior level of technology. I don't think that's true because a lot of the technology they use is from Germany. So it's likely that Spain is still coming from a less intensive capital state, or the Spanish consumers, Spanish households, Spanish firms are investing less per capita. Something you have to investigate empirically. Again, the Solow model is just a finger exercise, but it already gives you some insight into why countries are rich or poor if they have the same technology. Okay? Now, the Solow model also has a lot to say about the dynamics of convergence. And it turns out that this model, and I think Andreas will talk to you about that, I certainly will mention it, is that using the model and taking it seriously says that the rate of convergence to this new steady state is very slow. Okay, so it's about between 2 and 4% per year. So how long will it take to close half the gap? You go do the math. This is bad news. This explains why a lot of countries are still in some sort of convergence mode, okay, if you take the Solow model seriously. But the Solow model is limited. It's limited by its lack of micro foundations. I just told you that Germans save 25%. That's maybe a fact, but there's no reason it's written in stone. There's no reason that American savings couldn't go up or go down. And there's no reason why Chinese savings has to stay at 40%. Okay? So again, we have to question the lack of microeconomic foundations. Still, we can make very interesting statements about this. And we can push it a little bit further, and I'll introduce a concept to you right now called the social planner. If the social planner could actually set your savings rate, what would it do? What would be the best savings rate to set? This is a very interesting question. Okay, this was posed by Ned Phelps in the 1960s. Because back then we had a lot of communist governments, state socialism, etc. It made sense to ask what the state can actually control with pretty much accuracy how much to save and how much not to save. And you could induce maybe in a free market economy or a semi-free market economy inducements to make people save more or less. So it's a very interesting question, and Phelps got a Nobel Prize as well for this contribution. Okay, so he asked, how big is the red bar? In effect, who cares about capital? Who cares about all the material productive stuff we have? Do I want to have a machine tool in my backyard? No. But I want to see it being used to produce more for me? Yes. Okay? So the question is, what matters is the consumption. It's the complement of the savings necessary to sustain an equilibrium in the Solow model. So this is capital this is the complement of savings. It's consumption per capita. The red bar is how much, well-being do I derive from this outcome. So if you look carefully at that, you can see that it takes different levels depending on how much capital intensity I have. Okay, so Phelps' famous question was, what would I do? If I were the social planner, what would I do? And the answer is you set the slope of that production function equal to the slope of the capital widening line. Okay, you can see it just by eyeballing it that this thing gets bigger and bigger, but at some point, if you've hit a point where that slope is equal to that slope, you're not going to make things better, you're going to make things worse. Okay, so in that particular diagram, it wasn't exactly right, but you can show it formally. I wasn't trying to show it. So you set the marginal product of capital equals to the slope of this capital widening line, and we know what that is. That's the rate of growth of technology. It's plus the depreciation rate of capital plus the population growth rate. Okay? And in perfect competition, this corresponds pretty much to the return on capital, the rental rate on capital. So it says something about the interest rate. And we know the interest rate, nowadays is rather low. It's been low for many, many years now. It's not just monetary policy. It's probably also has to do with real stuff. So you might say it might have to do with some of these underlying factors. Maybe it has to do with demographics. Maybe it has to do with technical progress. So maybe A and N are not fixed. And anyway, those are just stimulating questions for future thought and research. We can still think about efficiency. Okay? And you can, in the section, you can probably mention the fact that if you're on this side, if this is the optimal point where the slope is equal to that slope, then over there I'm actually saving too much. The marginal product of capital per effective unit of labor is too high. too low, sorry, too much savings, and I could actually reduce my savings and make myself better off in a long run sense. Okay, so that's what the insight of the golden rule was by Ned Phelps. Okay, so in the long run, we're talking about these steady state facts. I'll finish up talking about these. Okay, in the Solow model, I'm able to exploit the properties of the production function to get a steady state statement about little y. It's not changing, even though it's a growth model. Y star is constant in the steady state, but output is growing at the sum of the rate of technical progress, growth, and the growth rate of the population. Okay, so that's why Solow got the prize for this, because we were unable in the 1950s to explain long-run economic growth. So Solow basically put it down. This is the best first cut at getting a model with neoclassical production to generate long-run growth and constant output capital ratios. Okay, so it's discipline, data, discipline, theory, and theory disciplines data. The dissatisfying or the unsatisfying part of this model is the fact that we still have growth in the economy per capita given by technology. Now, Solow actually shows this in another paper. He showed that long-run economic growth is mostly due to technical change and not to increases in capital intensity. But it's still kind of unsatisfactory for economists to be assuming the very thing that is making them excited. So this is the frontier. If you're interested, one of the most famous growth economists by the name of Philippe Aghion is coming to Berlin, and you should go see his lecture. Okay, I'll make an announcement later. It's in November at the Wissenschaftszentrum Berlin. And he's one of the biggest thinkers about this area. How can I make A endogenous? Remember, we've assumed it's exogenous. That's what Solow did, right? So if we want to do better, why do some countries generate all the research and some countries don't? Okay? So, again, you should finally, the last note is that think about y star and the current value of y. Think about that picture. If current y is less than y star, then y is growing towards y star. And if y is greater than y star, it's declining. So these are times when we still have growth, but we have decelerating growth in the second case, or accelerating growth in the first case. Okay? And we can approximate this attractor. Okay? And this was the so-called Sally-Martin, Barrow-Sally-Martin rule that I mentioned before, that if y is the steady state, and this is where we are today, the rate of change, or the rate of, if it's actually the, should normalize that by y, it should be the rate of change, not the absolute level of, not the change per unit of time, is a function of how far we are from the steady state. So the closer we get, the slower the convergence is, okay? And as a local result, this first order approximation says that it's equal to these parameters in the Solow model. So this is a very strong prediction, and this is where the Solow model falls, okay? Because if you take OECD countries, this would mean that countries that are rich should be growing very slowly, like the United States and Germany, and countries that are poor should be growing faster. Right? The farther you are, the more capital you're accumulating, the more productive that capital is, the more you're growing. It does work for the OECD countries. Okay, so here I've plotted GDP per capita in 1960, and this is the subsequent growth on average over the next, say, 53 years. So you can see there's a negative relationship. There's some guys falling off the map. Those tend to be countries that have had some political problems. I won't mention them. But there's a negative relationship. So it works for the OECD, but if you go into the developing world, forget it. So it doesn't work. And we see that because there are a lot of countries that are just persistently poor. If you assume they have the same production function, the model is no good. Okay? So there are several ways to get around that. I'll talk about it next time. You can assume that maybe every country has its own y star. It has its own production function, its own set of technology, and maybe corruption, maybe governance problems, governance advantages. okay? Then you can do what's called conditional convergence. This is an unconditional convergence statement. This says that every country should grow and achieve the level of per capita GDP that Germany has, just give them enough time, okay? And we can see from the world experience, this has not been a great prediction in the data. Okay, so we'll talk about conditional convergence next time, and I'll spend less time talking about the theory of models and get into the details of this model and the models that follow. Okay, thanks for your attention. I'll see you next Tuesday. Don't forget Andreas, okay, tomorrow.